Going to explain the basic compound inequalities. There are two types, the conjunction and the disjunction. The conjunction is associated with the word and the definition states that both conditions must be true, meaning that you're looking for a number that makes both conditions in the inequality true at the same time. The disjunction is associated with the word or, and the definition states that only one must be true. Only one condition must be true. So here's the basic example of a conjunction. So you can see that I've got this arranged, just written one time with the variable in the middle. Notice that 4 is actually less than 6. Both inequality symbols are facing in the same direction. And then the graph to represent this, you could just draw a little number line, and I've got 4, and I've got 6. And I should put an open circle at the 4, since that's the strict inequality, and then the less than or equal to at the 6. So I'm looking for all of the numbers between 4 and 6, so I would shade between the two. This would be my typical and outcome. So this number line shading represents all of the numbers that are greater than 4, but not including 4, up to and including 6. So the shading with the open circle, closed circle is directly related to the inequality symbol itself. But the number line graph with the two boundary points shading between is your typical standard and outcome. Interval notation, I have 4, I have 6, soft and hard. So it tells me that 4 is the strict inequality, not part of the solution set. 6 is included in the solution set with the hard bracket. And then set builder notation, I could open up the brace, X such that, and then you just basically simply recopy what's happened above, the basic inequality. Let's look at the disjunction. So the disjunction must be written with the word or. And I've got two separate conditions. So I'm going to draw my graph, and here's my boundary point of 4, here's a boundary point of 6. If I'm graphing all the numbers that would be, or expressing all of the numbers that are less than 4, x is less than 4, strict inequality. So I put the open circle at 4, and then I shade in the direction of negative infinity. Coming to the other side, the or, this is my broken or graph. I'm looking for all of the numbers that are greater than 6, including 6. So here I have the solid circle shading in the direction of positive infinity. So these are your two basic cases. Interval notation for the disjunction would look like negative infinity coming up to 4. They're both going to be soft. Since 4 has the strict inequality, I'm going to union this with 6 going to positive infinity with the hard bracket and the soft for the infinity. And then for set builder notation, you would just simply do x such that, and then you would just copy each. X is less than 4, or x is greater than or equal to 6. But the point that I was trying to make a minute ago, the graphs really tell the story with the two basic types. The typical and graph, you've got the boundary points and you're shading between the points. The typical outcome for the or, the boundary points shading away from each other. So you've got the broken graph in the middle. That's your basic example for both types, conjunction, disjunction. Let's move on to the types that are less straightforward. So moving on, let's look at the no solution, infinite solution first. And I think that the graph really tells the story. So here's my graph, and I've got a boundary point of 4, a boundary point of 6. I'm looking for all of the numbers that are less than 4, open circle, all of the numbers less than 4. I'll change to blue. All of the numbers less than 4, and I'm looking for all of the numbers greater than 6, including 6. Remember, this is my and, so both conditions must be true. That means I'm looking for a number that makes both true. No number exists to make both true. There's no number that exists that will make both true. So this is your no solution scenario. When the inequalities are presented in this manner, attached with the word, connected with the word and, you graph, you look at your graph and you see that you will never find a number that will make both conditions true. So this is where you would simply say no solution. And I've explained to you in words why. Math notation, for no solution, you really could just do the empty set. Set builder notation, I think we can just go ahead and go with the empty set. This is a no solution moment. No solution. The flip side, moving to the world of disjunctions, let's draw a graph. We've got 4, we have 6. All the numbers greater than or equal to 4. So let me go with blue again. Solid circle, where's my 4? All the numbers greater than 4, or all of the numbers less than +6, open circle. You can see that the arrows are going in opposite directions, surpassing each other. So I'm including the entire number line. So this is my infinite solution scenario. And then the world of integral notation, that's simply negative infinity to positive infinity with soft. And you could, for set builder notation, we could just say x such that x is all reals. That works. And then attach the braces to that. So there's your, we have our no solution, infinite solution scenario. And let's look at the last outcome, the strangest outcome, where you have to go back and refer to the definition to claim the solution range. So what happens when both arrows are facing in the same direction? And remember that the conjunction side means both have to be true, and the disjunction side, only one must be true. So let's analyze the graph. My first scenario, so I've got a 4 and I've got a 6. Let's see, open circle, all of the numbers less than 4, but not including 4, and graphing the other side, solid circle, all of the numbers less than 6 and including 6. So I have to go back and invoke the definition in order to figure out which range would represent the solution set. Notice that in this example, the arrows are facing in the same direction. All of the examples above, the arrows were facing in opposite directions. They were either traveling away from each other or toward each other. Here, they're both traveling in the same direction. Since both must be true, I have to go with the smaller range. So for this particular problem, my solution set is going to be all of the numbers less than 4, but not including 4. So here I choose the smaller range because the smaller range would contain all of the numbers that would make both inequalities true at the same time. And then interval notation for this is just simply going to be negative infinity up to 4, soft, soft with that. And then the flip side, the other scenario, drawing the number line, I've got 4, I've got 6, all of the numbers less than 4, open circle, all of the numbers less than or equal to 6, solid circle. Notice the arrows traveling in the same direction. The difference here, though, would be the words that connect the two, or the word that connects the two inequalities. The word or would be connecting on the disjunction side, the word and connecting on the conjunction side. So moving over to the disjunction side, definition states that only one interval must be true if you have to choose. So in this case, I can choose the larger range because I don't have to worry about both conditions being true. Only one must be true. So here my correct outcome would be all of the numbers greater than 6, including 6, and your interval notation would be negative infinity up to 6 with a soft and a hard